How to access our website. Go to any browser and type search creators. Click on the first link. Now you have entered our home page where 50k plus study materials are available along with 1000 plus project ideas. We have 10 plus expert members in our team and we also support 50 plus engineering domains. In navigation bar, select University study materials. There are three streams available: computer science, information science, and artificial intelligence and data science. For now, we will click on computer science. Now we will be able to access all the study materials of different subjects of different semesters.
Welcome back to Search Creators YouTube channel. In this video, we are going to look at the next topic in Module 2, which is Virtualization Structure, Tools and Mechanisms. In this topic, first we are going to look at VM architecture classes. After virtualization, a virtualization layer is inserted between the hardware and the operating system, converting real hardware into virtual hardware. What it means that the virtual layer is inserted between the hardware and the operating system. What happens if we insert the virtual layer in between them is it converts real hardware into virtual hardware. This allows multiple OSs like Linux, Windows, etc. to run simultaneously on a single machine. By doing this, it will allow multiple operating systems to run simultaneously on a single machine. There are three main classes of virtual machine architecture, which are hypervisor based virtualization, which is VMM, virtual machine monitor, para virtualization, host based virtualization. These are the three main classes of virtual machine architecture. Hypervisor and Zen architecture. What is hypervisor and Zen architecture? The hypervisor enables hardware-level virtualization by running directly on a bare metal hardware, which are CPU, memory, disk, network interfaces. It acts as an interface between physical hardware and guest OSs. Next, we are going to look at the types of hypervisors. Microkernel hypervisor, for example, Microsoft Hyper-V. It includes only core functions like memory management, processor scheduling. Device drivers and other components are external. The device drivers and the other components are external in microkernel hypervisor. Smaller hypervisor size, and it has a smaller hypervisor size. Next is monolithic hypervisor. Example VMware ESX. It implements all functions including device drivers, larger hypervisor size but with better performance and control. If we compare microkernel and monolithic kernel, microkernel has small hypervisor size. In monolithic hypervisor, it has larger hypervisor size. Along with it, it gives better performance and control. Next, we are going to look at the Zen hypervisor architecture. Zen is an open source microkernel hypervisor developed at Cambridge University. Separates policy like handled by domain 0 from mechanism handled by Zen. Like it separates policy from mechanism. No native device drivers like guest OSs handle device management directly itself. Virtual environment between hardware and OS. It is a virtual environment between hardware and the operating system. Next, we are going to look at the components of Zen. First component is hypervisor. Hypervisor. What is the description of hypervisor is core virtualization layer between hardware and operating system. Next is kernel. It supports guest OS execution. Next is application. Runs on guest OS instances. Next is Zen domain structure. Here we are going to look at one figure. In this figure we can observe the Zen architecture's special domain 0 for control and input output and several guest domains for user applications. Here we can observe that in this figure. Next is domain 0 or DOM 0. Privileged guest OS with direct hardware access. It is a privileged guest operating system with direct hardware access. Manages guest operating system instances like domain U. Controls resource allocation and device management. Like it controls resource allocation and device management. Next is domain U or DOM U. Unprivileged guest operating system instances running under Zen and cannot access hardware directly. In DOM, unprivileged guest OS instances running under the Zen and it cannot access hardware directly. Next is security considerations. In security consideration, domain 0 is the most critical component. If compromised, the attacker gain full access control over all virtual machines. Like domain 0, if it is compromised, the attacker will gain full control over the virtual machines. Security policies are required to protect the domain 0. Like certain security policies are needed in order to protect the domain 0. Next is virtual machine state management and rollback. Unlike traditional machines which follow a linear execution path, virtual machine execution follows a tree structure where multiple instances can be created at different states. Unlike traditional machines, like in olden days, which follow a linear execution path, the virtual machine execution follows a tree structure where multiple instances can be created at different states. Next is benefits of virtual machine state rollback, like error recovery, efficient system distribution, live migration are some of the benefits in virtual machine state rollback. Error recovery means rollback to a previous working state. Efficient system distribution means duplicate virtual machines for dynamic content. Live migration means moving running virtual machines between hosts. Next is challenges. Security risk in handling virtual machine snapshots and rollbacks. Need for strict access control and auditing. Some of the challenges in this are security risks are there in handling virtual machine snapshots and rollbacks and need for strict access control and auditing. Next is binary translation with full virtualization. Depending on implementation technologies, hardware virtualization can be classified into two categories, which are full virtualization and host-based virtualization. Full virtualization does not need to modify the host OS. Like in full virtualization, there is no need to modify the host operating system. It relies on binary translation to trap and to virtualize the execution of certain sensitive non-virtualizable instructions. It depends on binary translation to trap and to virtualize the execution of certain sensitive and non-virtualizable instructions. The guest OSs and their applications consist of non-critical and critical instructions in a host-based system. Both a host OS and the guest OS are used. In this, we can observe that the guest OSs and their application consist of non-critical and critical instructions. In a host-based system, both a host OS and the guest OS are used. A virtualization software layer is built between the host OS and the guest OS. These two classes of virtual architecture are introduced next. Next is full virtualization. With full virtualization, non-critical instructions run on the hardware directly while critical instructions are discovered and replaced with trapped into the VMM to be emulated by software. In full virtualization, non-critical instructions run on the hardware directly, whereas the critical instructions are discovered and replaced with traps into the VMM to be emulated by the software. Next is both the hypervisor and VMM approaches are considered full virtualization. Like both the hypervisor and VMM approaches are considered full virtualization. Why are only critical instructions trapped into VMM? Like why are they only critical instruction trapped? This is because binary translation can incur large performance overhead. That's why only critical instructions trapped into the VMM. Next is non-critical instruction do not control hardware or threaten the security of system, but critical instructions do. Non-critical instruction do not control hardware or threaten the security of the system, but critical instructions do threat and they have some security constraints in them. Therefore, running non-critical instruction on hardware not only can promote efficiency but also can ensure system security. Next is binary translation using VMM, Virtual Machine Monitor. Implemented by VMware and other vendors, VMM is placed at ring 0, which is privileged mode. Guest operating system runs at ring 1, which is unaware that it is virtualized. VMM scans and translates privileged instruction before execution. Code caching helps optimize performance but increases memory usage. Next is host-based virtualization. Runs on a host operating system rather than directly on hardware. The virtualization layer sits between the host operating system and the guest operating system. Guest OSs and application can run inside virtual machines while other application can run directly on the host OS. Guest OSs and application can run inside the virtual machine whereas other application can run directly on the host operating system. Here in this figure we can observe indirect execution of complex instructions via binary translation of guest OS requests. Here in this figure we can observe it. Next we are going to look at advantages. EACR deployment, simplified design, works on various hardware configuration. These are some of the advantages. Next, we are going to look at disadvantages. Lower performance due to multiple layers of hardware access. Like lower performance can be observed due to multiple layer of hardware access has been done. Requires binary translation if guest OS and host hardware have different ISAs. Higher overhead making it less efficient in practice. Next is para-virtualization with compiler support. Overview of para-virtualization. It requires modification of guest operating system kernel to support virtualization. Provides special APIs like hypercalls to replace non-virtualizable operating system instruction. Reduces virtualization overhead, improving performance compared to full virtualization. Unlike full virtualization, which relies on binary translation, para-virtualization requires operating system kernel modifications. Next is what is para-virtualization architecture? In this figure, we can observe para-virtualized VM architecture, and in this figure, we can observe the use of para-virtualized guest operating system assisted by an intelligent compiler to replace non-virtualizable operating instruction by hypercalls. These are the two figures. You can go through this. Next is a virtualization layer is inserted between hardware and operating system. We are seeing this earlier. In x86 architecture, the OS typically runs at ring 0 for privileged operation while applications run at ring 3. Para-virtualization modifies the guest OS to run at ring 1 instead of ring 0. The para-virtualization modifications which are the like it runs at ring 1 instead of ring 0. Replace non-virtualizable instructions with hypercalls to hypervisor VMM. Next, we are going to look at advantages of para-virtualization. Improves performance by eliminating need for complex binary translation. More efficient than full virtualization, like especially for workloads with frequent privileged instruction. More efficiency can be observed compared to full virtualization. Used by popular hypervisors like Zen, KVM, and VMware ESX. Next up, what are the challenges of para-virtualization? It requires modifying the OS kernel, making it less compatible with unmodified OSs. Like the para-virtualization required modification of OS kernels, which makes it not compatible with the non-modified operating systems. Like modification is very necessary for para-virtualization. Maintaining para-virtualized operating system versions is costly. Like it is not cost efficient, and maintaining para-virtualization operating system versions is very costly. Like OS update is required for modification. Performance benefits depend on workload types. Some workload benefits greatly while others do not. Like the performance cannot be predicted. Like the benefits depend on workload types only. Next is KVM, kernel based virtual machine. This is a Linux para virtualization system, a part of Linux version 2.6.20 kernel. Memory management and scheduling activity are carried out by existing Linux kernel. The KVM does the rest, which makes it simpler than the hypervisor that controls the entire machine. The KVM is a hardware-assisted para-virtualization tool which improves performance and supports unmodified guest OSs such as Windows, Linux, Solaris, and other Unix variants. Next, we are going to look at para-virtualization with compiler support. Unlike full virtualization, which traps the privileged instruction at runtime, para-virtualization modifies the instruction at compiler time. Like in full virtualization, we observe that it traps privileged instruction at runtime, but para-virtualization modifies the instruction at the compiler time itself. The operating system kernel replaces privileged instruction with hypercall before execution. The operating system kernel replaces the privileged instruction with hypercalls before the execution. Next is Zen follows this architecture where the guest operating system runs at ring 0 instead of ring 1 instead of ring 0. Privileged instructions are replaced with hypercalls to the hypervisor. Hypercalls function similarly to system calls in Unix, like using service routines. Next, we can observe an example. In this example, we have the ESX server for para-virtualization, like some explanation of VMware Pioneer, like on some explanation of VMware can be observed, like VMware pioneered the software market for virtualization. The company has developed virtualization tools for desktop systems and server as well as virtual instruction for large data centers. Like this is some basic theory, and in this figure we can observe the VMware ESX server architecture using para virtualization. You can put this figure, and some explanation about that figure has been mentioned below. Like this is all about the topic module 2 of cloud computing, which is virtualization structure, tools, and mechanisms. I hope you understood the concept. If you have not downloaded the notes, please download the notes from our website. The website link is in the description. Thanks for watching the video. Stay tuned for upcoming videos on module 2 of cloud computing. Please like, share and subscribe to our channel.